Okay, so another example that we have here about the polar non-rectangle. This one is just to get the limit. So we don't want to solve this, just find the limit. Just to do exercise on finding limit for polar. So find the limit of integration. So you have double integral where the integrand is not given, just r theta. Okay, and r d theta. And your region lies inside the cardioid. Okay, so what is the cardioid shape? The cardioid shape, remember that? Okay, so polar graph. So this actually, I'm taking this from the book of Engineering Maths 1. So this is the polar graph. So we have a lemma cone where the equation as given in general, you have the bean shape, right? The bean shape. Okay, and we have a cardioid, just like the heart shape or love shape, and we have a lemniscate number 8, and we have a rose petal where we have a cos n pi or a sin pi. So this one, for example, we have 1 theta, not pi, sorry, theta. So a cos theta, a sin theta. So if you have 2 cos theta, so diameter of this is 2. 2 sin theta, so diameter here is 2. And we have rose petal with 1 petal. This is 3 petals, and this is 4 petals, and so on. So for polar, so this is very important as well. So you should know this as well, because sometimes, just like this question, so they asking about the cardioid. So maybe for now you have no idea, you don't remember the cardioid shape. So what is the cardioid? So this is the cardioid, 1 plus cos theta. So find out the positive 1 plus. So you have 1 plus 1 cos. So you have this bean shape like this. Okay. So meaning that when you draw it, you have something like that shape. Okay, and should be symmetrical. Okay, it is supposed to be, I should draw properly, right? So yeah, this is the cardioid, and okay, so that cardioid, okay, this is on y-axis plane, and then the region lies inside the cardioid, inside this cardioid, and outside the circle with radius 1. So circle with radius 1. Circle with radius 1. Maybe have this. Okay. Outside the circle. Outside the circle, inside the cardioid. So it looks like your R is that one. Alright. So now you have to determine the theta and the R. So as I mentioned before, normally we have the R, the theta. We have to do R. So the theta here should be constant. Okay. And your R here is supposed to be not constant, because now you have your region is not part of the circle with radius. I mean, your region here is not part of the circle centered at the origin. It's the combination between the circle centered at the origin and the cardioid, where it is not a circle. Okay, even though the function is in terms of polar, so it is a function here. So that's why we consider this. The limit of this is not all constant. They are not all constant. Because we just sketch it, so we have no idea whether our sketching here is exactly correct or not. Okay, so now you have to find out the intersection point between the circle and the cardioid. So then you have to have the cardioid is the equation of cardioid is 1 plus cos theta, and the equation of the circle radius 1 is r equal to 1. So now we want to solve this simultaneously because we are looking for the intersection point, because we want to make sure where they will intersect each other. It looks like over here, but is this true? Because we just sketch it, so maybe your sketching is not exactly correct, right? So then when you solve that, you have 1 plus cos theta equal to 1. So cos theta equal to 0. So theta is cos 0. Okay, so cos 0. Just ask yourself, cos of what angle? The answer is 0. So we have the graph here. So let's say we only consider one cycle only. So this is pi. So this is pi over 2. Okay. This is 3 pi over 2. So it looks like the value of theta is at pi over 2 and 3 pi over 2. So cos 0 at pi over 2 and also 3 pi over 2. So meaning that the intersection point here is located at theta equal to 90 and 270. So my sketching is not correct. So then we have to correct that. Okay, so because we know that the intersection between the circle and the cardioid should be on 90 degree and 270. So you have to make sure they intersect on this point. Okay, at this point. Okay, so now look at the equation. So we want to know what is the value at. You have to know the value on the x intercept. Okay, so since in polar we don't really interested to know the value on the x intercept or y intercept, because this one we know that this the intersection point there, this one is 90 degree, and we have theta equal to pi over 2, and the other one you have 3 pi over 2 down there. So where is actually the region that you have to shade? So outside the circle, inside the cardioid. So this is one. Okay, so now we are talking about the theta. So you have the r d theta, right? Theta constant. So as you can see, your region is lying at the first quadrant and fourth quadrant. Okay, so what you can have is, it looks like your theta is you cannot put the limit to be 3 pi over 2 to pi over 2, or in degree you can 270 to 90. So it is not correct, because for interval, so the lower bound should be smaller than the upper bound. Then if you put this like this, so it is incorrect. So what you have to do is, it looks like you have to split the region. So firstly, you have to deal with the so this is incorrect, right? So you have to deal with the first region where you have 0 to pi over 2, which is the first quadrant, 0 to pi over 2, only this region, and then plus another angle for 3 pi over 2 to 2 pi. So this is fourth quadrant. So it looks like you have to compute two different double integral, where the first, your theta is 0 to pi over 2, and the second double integral where your theta is 3 pi over 2 to 2 pi. Okay, so when you want to obtain the double integral here, it looks like you have to split into two. R multiplied by r d theta. So your first theta 0 to pi over 2 plus, and you just copy everything, will be the same, r d theta, And now your theta is from 3 pi over 2 pi. So it looks tedious, right? Because you have to, it looks like a single region, but because of the way you want to use the lower bound and the upper bound, you have to split them into 2. Okay, actually you have a more simple way rather than you just split into 2 integrations. Okay, so what we can use the negative theta. Okay, you know that this one is 90 degree is pi over 2, right? And you can also give a new name for this where you deal with the negative. So we have, instead of we have 3 pi over 2, you can also use minus pi over 2. You remember about the polar? Polar, when you have negative angle, it means that you have the clockwise direction. So negative 90, you have a clockwise direction. So this one. So meaning that this is 270 degrees. So 270 degree or in radian is 3 pi over 2. It is the same as negative pi over 2. So now, if we put the angle, the limit of theta in terms of negative pi over 2, okay, actually you have negative pi over 2 to 0, right? That is for the fourth quadrant, isn't it? Because from the smaller value to the larger value, and then from 0 to pi over 2. So in terms of the value itself from the smallest to the, from the smaller one to the greater one, so it is possible, right? So negative pi over 2 to 0, telling you the fourth quadrant, and from 0 to pi over 2, it's telling you the first quadrant. So when you combine them all together, so the theta can be rewrite into an interval where you have theta from negative pi over 2 to pi over 2. So this is possible. So what I want to say here, if you proceed with these two integration, where is it? This one. So it will more messy because you have to compute the double integral twice. But you can simplify your work by rearrange your limit of theta. We just have the f r theta multiplied by r d theta, and now you just apply a single theta where negative pi over 2 to pi over 2. Okay, or in other words, in degree, negative 90 to 90 degree. So negative 90 to positive 90, telling you from fourth quadrant and also first quadrant. So I hope that you understand that. So that is for the theta. Now we want to look at the how can we determine the limit of r. So we know that to determine the r is the same as we done before this, where you have to provide the line starting at the origin. Okay, you can provide many lines just to make sure you have the same lower bound and the upper bound for all over the region. So now r. So when you walk slowly from the origin, so it's nothing, right? But then the first point that you can see is here, over here, 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 here. So that all that points are lying along the r equal to 1. And then you keep moving along these lines, and they are all end up at this point, and that points are lying on the r equal to 1 plus cos theta, which is cardioid. So now you know that your limit limit of r is from 1 to 1 plus cos theta. So you can see that it is not they are not, I mean all the limit are not constant. Okay, so that is the answer, because we just want to determine the limit.